All right, I think we can get started with continuing the morning session. So the next talk will be given by Rebecca Flint from Iowa State University. Rebecca, please.
All right, thanks so much. Thanks for everyone to coming, and thanks for inviting me, as I've really enjoyed this conference. So I'm going to tell you today about some work looking at two-channel Kondo material or Kondo insulators. So I've been working in the two-channel Kondo model for a long time now, and we found something I think is really interesting, which is the possibility of finding mobile Majorana zero modes in these kinds of systems. And this work was done with my student Milan Konyaka and my former postdoc Victor Quito. It was all funded by Department of Energy. And while I'm an expert on the two-channel Kondo model, I like to think, I'm definitely not an expert on these topological excitations. So I'm really very interested in hearing what people might have to say about what further things we could do with this. So let me first give a very simple introduction to Majorana zero modes, since we have many different audiences. So Majoranas are real neutral fermions. You can combine two of them to form a complex fermion and use them to encode a two-level system that could be useful for topological quantum computation. And here I'm talking about localized Majorana zero modes. So in the abstract, they should commute with a Hamiltonian to give 0, and they should be at 0 energy. But in real life, they'll probably have some kind of localization length. And these are non-abelian anyons, they're Ising anyons. And if you exchange the two defects adiabatically, sufficiently far away from each other, then you'll get this kind of Ising anionic statistics. So there's been many different proposals for how you could realize Majorana zero modes. I'm not going to survey them at all. I'm going to talk about something totally different, which is how you can get these in two-channel Kondo physics. So this two-channel Kondo model is the simplest example of overscreened Kondo physics. We've heard a little bit about it before, but I like to give this kind of picture so you can really get a physical picture of it. So one place where you can get the two-channel Kondo model is if you have an ion with 2 f electrons, like praseodymium, and it's in a sufficiently high symmetry. So here in cubic symmetry, you can get a ground state non-Kramers doublet that's actually non-magnetic, so it has no dipole moment. And you can plot the density of the f electrons, and you see that it's got 2 degenerate shapes. So one is kind of elongated and one is kind of squashed. And if you look at the conduction electrons that can screen this, they're also, one is kind of elongated and one is kind of squashed. And in cubic symmetry, these are degenerate. And so essentially, this is a pseudo-spin 1/2 doublet with 2 different quadrupolar shapes. And you can screen it with the quadrupolar moments of the conduction electrons. The conduction electrons also have spin, and so this here is acting as the channel. So your up and down conduction electrons form 2 different channels to screen the same local moment, and that causes overscreening. And so this gives you a quantum critical regime in the impurity. So this can be really carefully looked at in the impurity, and it's known that you have a 0-point entropy of 1/2 R log 2, which is associated with a single Majorana fermion at the location of your two-channel Kondo impurity. And so this point here, where you get this quantum critical behavior, is when your 2 channels are equal to one another, and this is something you naturally get when you have this kind of non-Kramers ground state doublet. And so here's the question, is this a Majorana zero mode, like we talk about being potentially useful for quantum computation? And the answer has generally been no, right? So first, it's typically found in metallic systems. So if you have 2 of them, the Majoranas can talk to one another. There's a nice thermodynamic analysis by Toth et al. That showed that in all of the materials that we've seen, there's no 1/2 R log 2 entropy. You can imagine gapping out the conduction electrons using superconductivity or something else like that. And as long as you have a sufficiently strong Kondo interaction, you could still get this kind of Majorana physics, and they wouldn't talk to one another. But you still have the problem that these are defects. They're very difficult to move around. You definitely can't do that adiabatically, so there's no possibility of braiding. And so this is what we ended up looking for, right? So we thought we have two-channel Kondo physics. We expect, so we know from the single-channel Kondo effect that if you take out a spin and create a Kondo hole, that effectively behaves like a Kondo impurity. So we expect we might get something similar when you looked at defect states in the two-channel Kondo lattice. And fortunately, we can get a two-channel Kondo insulator if we're specifically at quarter filling. So it's an analog of the single-channel Kondo insulator, but with sort of a twist due to the two channels. So, okay. So we're going to go from the impurity to the lattice, and that makes life much harder. So I'm going to tell you only a little bit about what we know. So we can solve this exactly in the large N limit. It can also be treated numerically in one dimension or infinite dimensions. There's many possible phases, and I'm going to focus on just one of them, which is essentially a channel ordering. It's basically a channel symmetry breaking heavy Fermi liquid or Kondo insulator. And in our work, we call it hastatic order. There's some work by Hoshino, Atsuki, and Kuromoto that calls it diagonal composite order. It's the same thing. So I'm going to continue to call it hastatic order, and it may well be a non-Fermi liquid, as was discussed in Chanda and Seti's talk a little bit. So let me give a sort of quick picture of what it is, and I want to take a step back and look at the picture of normal one-channel Kondo lattices. And so this is my theorist picture of what's going on there, right? So you have a ground state that's a Kramers doublet. So for like cerium, you have 4f1, and it flips the spin by having virtual valence fluctuations to an excited state, which is a singlet. And I can use an auxiliary boson to represent this excited state, or effectively to represent the Kondo singlet itself. And this doesn't carry any quantum numbers, so the hybridization doesn't break any symmetries. Everything develops as a crossover, and life is fairly straightforward. So now I'm going to start with a non-Kramers doublet ground state, like I showed you before. And it's going to have similar virtual valence fluctuations, but these are going to be to a system with an odd number of f electrons. And so their time reversal symmetry guarantees you that your excited state is a doublet. And so this guarantees you the two-channel Kondo effect. And the way we deal with it is, I'll say, no big deal. I just have two excited states. I introduce two auxiliary bosons to represent this. And I package them together into a spinner, because that's the structure of this excited Kramers doublet. And effectively, this is representing this excited doublet. You develop an occupation of it when you undergo the Kondo effect. And then you have a little moment that can pick a direction to point. You can alternately think of this in the Kondo limit as having your Kondo singlet having a channel label. And so your hybridization is actually essentially a non-gauge invariant spinner, which leads to lots of interesting consequences. And one of them is that you can develop basically a moment orientation at a phase transition, because you are breaking a real symmetry. So these kinds of systems are found in real materials. So we originally introduced a hastatic order with Piers Coleman and Premi Chandra to try to explain the hidden order phase in uranium, ruthenium 2, silicon 2, which I'm happy to talk about, but not right now. And then there are proposals in these praseodymium 1,220 materials. These are also two-channel Kondo systems with a non-Kramers doublet ground state. And so they have possible non-Fermi liquids and Fermi liquids and interesting physics there. So this is basically just to say, look, this is not totally abstract. There can be realizations of this. So now let's talk about the kind of physics you can get when I get in this large N, and say in the large N limit, although it will survive past that. So essentially, I'm forming a channel-ordered Kondo singlet. So here's just a single site where I have a local moment I'm representing with an F electron, and then I have two types of conduction electrons for my two channels for the spin up and the spin down. And so here I've chosen to form a Kondo singlet between the local moment, and the spin-off electrons. And so then I have a choice when I go to the lattice of how do I pattern my lattice essentially with these Kondo singlets. And so the simplest thing you can do is just choose all of them to be with one channel. So this is essentially a Faro order of this. We call it ferrohostatic. And so in this picture, it's very simple. Oops, sorry. In this picture, it's very simple. Only your up electrons hybridize, they become heavy electrons, and your down electrons are decoupled. You can then also arrange this in an anti-Faro way. And so you put, sites on the A sublattice hybridize with the up electrons, sites on the B sublattice hybridize with the down electrons. And this all seems straightforward until you remember that these channel Kondo singlets actually have a Spinorial label essentially. And so when you apply time reversal to these spinners, you have to be careful because they are spinners, right? And time reversal acts differently on spinners than it does on vectors. So if I do an antiferromagnet, I can essentially make two sublattices, and then I have a nice anti-unitary time reversal like symmetry. That's time reversal followed by swapping the two sublattices or translation by one unit cell. If I want to do that for these channel orders, I need actually 4 sublattices to have a time reversal like symmetry. So my spinner essentially has a direction, it's given by some angle theta and angle phi, but there is this extra SU2 angle out here. And that does have real physical consequences, which I think is really cool. So basically what this tells you is that if you really want to preserve something like time reversal and do something like antiferromagnetism, you need 4 sublattices. So here, hybridize with up with a sign plus, hybridize with down with a sign plus, and then this one is 2 time reversals of this one, so it picks up a minus sign, and this one also picks up a minus sign. And then I'm back to repeating myself. And so there, I have 4 sublattices, so I've actually broken an extra symmetry just by the spinor sign. And so this is an inversion symmetry, and you can just do the naive thing and have 2 sublattices, and this will actually break time reversal symmetry, but in a very subtle way. And we've seen all of this in the microscopic picture, and you actually see, so let's see how we can really think about this in terms of order parameters. So the channel order parameter is an SU2 spinner. It's not gauge invariant, but I can construct gauge invariant order parameters. This is done in this Landau theory analysis of my student. And so this first order parameter is an on-site local order parameter. It's essentially the excited moment in that excited state. And so it's a moment in the channel, it has a channel moment. Here is how you write it in terms of the original conduction electrons and spins. And this has been known for a while, right? But there is also an additional non-local order parameter that arises essentially from interference between spinners on different sites and tells us the difference between these 4 sublattice and 2 sublattice arrangements, which have the same composite moment arrangement. And so here, it's essentially, oops, I missed a spin degree. There's a sigma Pauli matrix vector in there that I missed. But it's non-local because it involves hybridization on sites I and J, and then you have an F electron string essentially between the 2 of them. And what's really neat about this is that you actually do find it. So we did a DMRG study of this, and this order parameter also shows up. Okay. And in the mean field picture, both of these order parameters will develop at the same time as the spinner condenses. And so everything develops at once, but beyond mean field theory, you can imagine splitting these so that you can develop an amplitude of the excited moment first, and then maybe you develop the composite moment, and then maybe later you develop this sort of non-local spinorial interference, and so you'll break different symmetries at these 2 phase transitions. Okay, so we looked at this in the mean field, and this is just a picture to show that we do really get all of these. And the main point here is you can look at the phase diagram versus conduction electron filling, and near quarter filling, you get anti-ferrohostatic order, and exactly at quarter filling, it's a 2-channel Kondo insulator. So this is large N. You really want to know what happens in real life where N is equal to 2. And so here is the numerical work. This is numerical work by Hoshino, Otsuki, and Kuromoto doing DMFT in infinite dimensions. And so they find ferromagnetism and antiferromagnetism, but they also find this nice big region of anti-ferrostatic order near quarter fillings, which is NC equals 1, because you're going to have 4 different types of conduction electrons. Plus you find composite pair superconductivity. It's really neat. There's a lot of interesting stuff here. I'm really just focusing, though, on this one phase. You can also do DMRG in 1D. So there's an older paper from 2005, which also found the quarter filling antiferrostatic order. But we redid this, we revisited this recently in this archive paper and found basically you get static density waves almost everywhere at strong coupling. And particularly at quarter filling, you get an antiferrostatic Kondo insulator. And you see signatures of this phi order parameter in there as well. These are, of course, all algebraic because it's one-dimensional, but you really do see that you have this kind of physics. So it's very plausible, at least in the model, that you have a antiferrostatic 2-channel Kondo insulator essentially at quarter filling. You see it in infinite dimensions, you see it in 1 dimensions. I really believe that you're going to see it in 2 and 3 dimensions in real life. So, okay. All right, so now let's take a look. So this is our motivation, right? So now we have a 2-channel Kondo insulator, and we want to look at defects. And our motivation is that Kondo holes in the single-channel Kondo lattice act like Kondo impurities. They get screened and the like. Does something similar happen in the 2-channel Kondo lattice? That's the question we want to answer. And then can we get something new? And my answer is yes. So I'll show you that when we put defects in the hastatic order parameter, and so these will end up being skyrmionic defects because they're defects in this sort of spinner, in this composite moment essentially. They will host defect states that are half-filled, F-like, and have a 2-channel Kondo interaction with the remaining heavy electrons that puts them in the Kondo, in the regime that can host a Majorana physics. So, and they're mobile because they're not something that's sort of intrinsic to the material when you grew it. Instead, they're a topological defect that's really quite smooth and very likely very weakly pinned to the lattice. So you can, in principle, move it around, and then you can really have these 0 modes. Okay, so I'm going to show you a relatively simple mean field model, but I want to argue that the results are going to be very generic. So for this simple model, I'd really like to just have a single defect state. So I'm going to pick a sort of particular model where I have a Kondo insulating gap opening at quarter filling just at a single point. So to do that, I need 4 sites per unit cell. So I'm going to pick this square octagon lattice. So here are the 4 sites per unit cell, and I have hopping within the squares and between the squares. And here I'm picking a particular point 2t equals 2t1, but I actually get this quadratic band touching at the gamma point at quarter filling for a broad range of hoppings. Okay, so this is my point. Now I have a quadratic band touching at quarter filling, and so I expect when I open my Kondo insulator, my defects might just have a single defect, and that's what we'll find. So now let's put on hybridization, and I want to preserve time reversal symmetry, so I'm going to do this 4 sublattice hybridization, where I put basically up composite moments on these 2, but they have opposite signs. That's why they have different colors, and vice versa on these 2. And then I stagger the lattice like this. And when I do that, I can then calculate my heavy band structure. And let's zoom in to near the Fermi level. And so here I've opened up a Kondo insulating gap around the Fermi level. And so this is the bands, these are our density of states, and we'll show the impurity states are at equals 0, or at the Fermi level. All right, so let's now look at the defects. And so first, I'm going to walk you through the Kondo hole defect, which I think is the less interesting case, but it's a little easier to understand. And we did kind of a crude study of this. So what we did was we took out just a single site, so there's no F electron there anymore. And then we put this on a big real space lattice with just one Kondo hole and diagonalized it, and you find that you essentially get two types of states. You get delocalized bulk heavy electrons and a single impurity state that has a spin label, and these have channel labels as well. And so let me actually show you how we know we have a defect state. So we plot all of our states versus the pseudo-momentum, and we find a single state in the gap, and we can plot its F weight. And so notice here is where the defect is on the A sites, and the weight of this state is almost purely on the C sites. So this is not on the defect, but is associated with the defect. Then the weight of the state falls off exponentially as you go away. You can see this. We calculated the modified inverse participation ratio, which just uses the F weight of the wave function here. And so this tells you essentially how localized the state is. So here's our localized state. Here's all the other states. And we did this on with periodic boundary conditions, so we have no surface states. All right. So what we have is a localized state that's exactly at 0 energy, and it's basically pure F state. It's actually, I think, like 96% F from our calculation. There's a little bit of conduction electrons in there, but because it's a F state, those are guaranteed to be half filled, right? They have a very, very strong U. We're working in the Kondo limit where those are really coming from local moments. So this is the pseudospin 1/2 defect state, right? And so now I can ask, what's its interaction with the rest of the heavy electrons that are in these sort of bands on either side? And so you have to go beyond large N. So large N gives you this quadratic mean field theory, but you can include 1/n fluctuations or Gaussian fluctuations and use this to calculate essentially a matrix of Kondo interactions between your conduction electron, your heavy conduction electron spins now, and your impurity defect spin. So this is a very big matrix, which we calculated in real space. So I'll tell you a little bit. I don't want to go through the details, but please feel free to ask me about it. So we have a spinner that has a phase that we can essentially gauge out and work in radial gauge. We have amplitude variations. We have angles, theta and phi, and there's a constraint field that also will fluctuate. And so we calculate the propagator for these, which is essentially this guy here, and use this to yield the Kondo interaction. And so we can look at this in a couple ways. It's a big matrix. So the first thing we looked at was just looking at the diagonal Kondo couplings, which are already diagonal in channel. So they're diagonal in pseudo-momentum. And they look a little bit different. These dashed lines are the averages of these. And what you really want to do is diagonalize these to get your sort of dominant Kondo interaction eigenvalues. And so this is the eigenvalue of basically diagonalizing this really big matrix. And so we find two large eigenvalues, which are just in channel 1 and channel 2. So we have a 2-channel Kondo interaction of our local pseudospin 1/2 defect, but it's pretty anisotropic, about 25%. So we don't really expect Majorana physics. We expect single-channel Kondo physics here. And I should mention, we did a very crude approximation where we basically only changed the state on the location of the Kondo hole. I think this is probably an overestimate of the anisotropy, but nevertheless, let's move on to the more interesting case. And so we have our static spinner. It's easiest to just look at the composite moments. And so they behave just like magnetic moments. They have an SO3 order parameter. And in 2 dimensions, their stable defects are going to be 2-dimensional skyrmions. And so we can form a stable topological defect that's a 2D anti-ferrohastatic skyrmion. Here I'm just showing you what the A sites look like. The C sites will look the same, and then the B and D will have the opposite spin. Okay. And so we can enforce this structure on the orientation of the spinners by hand, and then see what we get for our defect states. And so here I'm first showing the F weight. Again, this is like 96, 97% F. And this is just taking a cut across the skyrmion here. So you see it's sort of delocalized everywhere across some kind of central plaquette. And it falls off again exponentially, but it's much, much smoother. So I really expect channel symmetry to be preserved here. And I can again look, here is the defect state sitting in the gap, and the inverse participation ratio again shows that it's localized. So again, well localized, F in character, guaranteed to be half filled. So this gives us, again, a pseudospin 1/2, and we can again calculate our impurity Kondo coupling, and we get a much different looking picture. So this is again the distribution of the diagonal Kondo couplings, and the average, which would be the S-wave channel, is basically less than 1% anisotropic. We take the eigenvalues. Again, we find two big, basically isotropic eigenvalues. So there's a little bit of channel symmetry breaking, and it does seem to survive for large lattice sizes. Okay. Okay, so now I have a two-channel Kondo impurity sitting in my in the center of my skyrmion, essentially, and interacting with the heavy bands via an isotropic two-channel Kondo interaction, or channel symmetric two-channel Kondo interaction. So that's basically what I want, but I have to be a little more careful. If you're familiar with Kondo physics, you should be like, okay, but this is an insulator, so, you know, do we really have actual Kondo screening? And, oh, sorry, this is, right. Okay, so you do need a threshold Kondo interaction, essentially, to put you into this regime where you see the two-channel Kondo physics. So if your Kondo interaction is strong enough, basically you're all good to go, you'll have a Majorana. And turns out that's basically guaranteed. And here's the reason. Okay, so first of all, we can find the impurity Kondo coupling. It's the original bare Kondo coupling, sort of generically speaking. And then you can use that to calculate the impurity Kondo temperature, Ti. And essentially what's happened is you had a flat conduction electron band density of states that gives you essentially your normal TK for the original Hess-static order essentially turning on. And then once you open up the Kondo insulating gap, you've opened a gap, but you've piled up those states basically right on the edge of the gap. So the states are still there. And so you have, if you on average, and actually get a sufficiently strong Kondo interaction to be in this quantum critical Majorana regime. And you have a sufficiently low anisotropy that you expect to have a really large temperature regime of Majorana behavior. So this is kind of our cartoon where actually the separation between these two is basically non-existent. So essentially, as you form the localized defects and form the two-channel Kondo insulator, they're going to start to be screened essentially immediately. And they'll then host these kind of Majorana zero modes below TK down to some kind of crossover scale Tx that's going to be pretty low. It grows quadratically in the deviation from the two-channel Kondo symmetric point. So that's the basic idea, theoretical idea. So now I want to talk about making this experimental, and here's where you see this is a bit of a long stretch, but experimentalists are so inventive. I love to give them all kinds of possibilities that I think are totally crazy. So here's your first step, right? Find a two-channel Kondo insulator. So you need quarter filling, you need a non-Kramers doublet ground state, and you need a sufficiently strong CF hybridization so that you're in the Kondo, you're forming a two-channel Kondo insulator instead of an antiferromagnetic light metal. So you can do this in cubic symmetry. So this, maybe you look at these praseodymium titanium 2 aluminum 20s. They're not at quarter filling, so you're not quite right. I think this material is very interesting. Thulium selenide. It's a non-Kramers doublet material that's mixed valent. It seems to open up a Kondo insulating gap at low temperatures, right at the Fermi level. but it is much more complicated. There's definitely more than 2 channels, and it's very mixed valent. So you may not get this sort of 2-channel Kondo model. You might get multi-channel Kondo model, and actually, then maybe you have something that's not a Majorana 0 mode, but some other kind of parafermion. So there's all sorts of possibilities. In tetragonal symmetry, we have this proposal for uranium, ruthenium 2, silicon 2. Again, it's not at quarter filling. You have an XY-like order parameter in tetragonal symmetry, so your defects will be vortices, but these should also have the same kind of localized defect states. And so, okay, say you found the material. Now you need to make the skyrmion defects. They're not going to sort of develop naturally. They're going to cost energy. But they are essentially magnetic skyrmions with really weak magnetic moments. So if you put a layer of a magnetic skyrmion material on top, then that's going to, and cool your system down through the Kondo temperature, that's going to essentially induce and freeze in a hybridization skyrmion as well. And so then you can, if you can move around the magnetic skyrmions and do it very slowly, you should also be able to move around the hybridization skyrmions. And then you can say, okay, well, do I actually have these localized defects? So you can measure that with STM, if you can measure sort of through the magnetic material. And the signatures will be that you get a localized defect state, so the size of the defect state is smaller than the size of the skyrmion. And you'll see that the defect state is F in character, so if you do STM, you see a Fano line shape. So all that I sort of know well enough to propose. The next step I could definitely use some help with, because you want to then be able to manipulate and braid the defects and use that to prove that they have a Majorana nature. And I could find a bunch of papers doing it for superconductors, but not for non-superconductors. And so if anyone has any ideas, please come talk to me. All right, so at that, I'm just going to sort of put up my conclusions. This is essentially the first realization of Majorana 0 modes in Kondo systems. We showed it in a simple model, but I believe the results are very robust. And I talked about sort of some possible realizations in uranium, ruthenium 2, silicon 2 films. You could also realize 2-channel Kondo physics in other systems like quantum dot arrays or add-atoms, which I think are a little bit more difficult still. All right, and with that, I'll stop, and I'm happy to answer questions. Thank you.
Thank you, Rebecca. Very, very interesting. I have a question about the Majoranas. So if I understand right, the way that you do it, you essentially map this model to a 2-channel Kondo-like problem,
yes.
And then you gap out the lead. So the lead is the whole system is already gapped. Now, usually, so the point is the following. Usually, Majoranas come in pairs. If you have like a type chain, it's on either end or so. Yeah. In the case of the usual 2-channel Kondo, the way that I understood it was this one Majorana is at the impurity, and the other one is sort of delocalized in this gapless bulk. But your bulk isn't gapless. So where is the second Majorana?
I guess I thought it was on the surface. Was my understanding of my usual Majorana, that it was not necessarily nearby, but delocalized to the surface.
So you will have one at the impurity and one somewhere at the boundary of your system.
That's what I think happens. Okay. Yeah.
Okay.
So does that mean that they're going to be surface states, gapless surface states?
Probably. Okay. Again, we can't see them in like the mean field, so I didn't calculate them because I don't really have an ability to really like directly see the Majorana here.
So let me ask. So let's suppose you have 2 of these Majorana modes. So that should define a qubit 2-level system.
Yeah.
So what are the 2 levels? So how do I? Do they differ in the parity of the number of electrons?
Yeah, they should. I think
they should.
Yeah, I mean, it's not coming directly from electrons, so this is where I have a little trouble as well.
Well, so how about this? So should there be a 0? Can you tunnel an electron into the Majorana mode the way you can in the superconducting one? Should there be a 0 bias tunneling anomaly?
So you should see some anomaly, but it's not going to be directly tunneling. What it's going to be is like co-tunneling, essentially. I'm not entirely sure how this reflects in the Majorana, but you can't tunnel directly into an F electron in this kind of Kondo picture because it's not really an electron. It's an emergent fermion that's come from the spin. So what you do there is you do a kind of co-tunneling where you flip the F electron and add the conduction electron at the same time, and that's how you get that Fano line shape. So I don't know what that will do to the Majorana. I think that's a very interesting question.
Okay, thank you.
Yeah.
Maybe I can follow up on that. So the Fano line shape by itself, can one really say, if I didn't know anything about a system, is that really coming from Majorana, or is it?
No, I don't think that tells
Yeah,
you.
would not be very direct, right?
Yeah, that's not very direct. So Fano comes from the fact that you just have two ways of tunneling in, one into the local F and one into the C's. And so that just tells you that you have some kind of defect that's made from spins there.
Yeah, right.
So
I wonder whether there's some collective object locally that one can probe. You can convolute this Majorana with a hybridizing Majorana.
Yeah, maybe.
Thanks for the nice talk. So in usual bulk systems which are gapped and have Majoranas, there's usually a way to understand why they cannot be deformed into an atomic insulator limit in terms of some singularity in momentum space that is captured by topological invariant. Can you shed some light on what is the singularity or non-analyticity in momentum space that would capture the topology?
Intrinsically, this is coming from a local defect, so I don't think it's well described in momentum space, right? Like this is, yes, there is another Majorana somewhere else, but this Majorana is on this particular defect, so it's really only well described in real space.
That's the block in my thinking. So it seems like it's possible to deform this to an atomic insulator, but then that is dissonant with the intuition that we have from usual Majorana, localized Majorana systems, where the Majorana comes from an inability to deform it to an atomic insulator or
I guess I think so maybe a better analogy is to think about like a half quantum vortex, right? Because it's in a topological defect. So I don't know how you connect that to an atomic insulator or not, but that might be a good way to start thinking about it.
Thanks.
Any other questions? Comments? There's one there. Well, there's a mic.
Can you construct an operator for this mode that is self-adjoint?
No, so I don't actually ever see the mode itself, right? I see this pseudo-spin 1/2 defect, and then I say it has this two-channel Kondo interaction, and this must be a Majorana. So within the two-channel Kondo impurity, you can construct a Majorana fermion that is essentially left over. You basically represent your spin in terms of 4 Majorana fermions, 3 of them hybridize with the conduction electrons, and then you have 1 left over. So that's sort of the typical construction.
So maybe this is related to the question just before, but in the single impurity case, it sort of seems like the Majorana is built out of degrees of freedom that are spatially localized near the impurity, whereas we might like it to be built from everything. So are these new ones kind of built from spatially delocalized degrees of freedom?
I mean, they're mostly built from localized degrees of freedom, right? So they're built from, like, if we look at the defect states, those are coming from mainly F states nearby the defect location, and it hybridizes with conduction electrons that are much more delocalized. So I don't know what to say about that spatially. Those are pretty delocalized. So it's coming from both of them.
Any other questions, comments? So maybe I just want to make sure that I understand this restoration of the channel symmetry, sort of having some mental picture. So do I understand it correctly that if you have a skyrmion, from the perspective of this defect, you're sampling through both channels if you look at the environment? Is that roughly the right
so like
way?
if you think about it, I don't know if I have a, so I want to put, right, so you have to think about what it's on the background of, because you've already sort of broken the channel symmetry. Maybe, okay, well, here's fine. Right, so I have these two kinds of states, right? And I put channel symmetry up on these guys and channel symmetry down on these guys, because it's an anti-ferro kind of channel symmetry breaking. But if you look sort of on average, the channel symmetry is preserved. And I think that's why if you put the Kondo hole here, that's really pretty strongly breaking the channel symmetry locally near the impurity. And that's why, because it's put on like one of these, and so on average, your channel symmetry near here is not so preserved. Whereas the skyrmion is very smooth, and it's basically averaging over all of the different
and therefore
channels.
you don't require very specific placement of the impurity.
Yeah,
Yeah,
no,
okay,
that's exactly it.
Thanks very much. I don't see any hands raised, so let's thank Rebecca one more time. All right, so the next talk will be given by Ming Yi from Rice University.
All right. Okay. Thank you, Timel. And I want to also begin by thanking the organizers for giving me a chance to attend this workshop and to show you some of our most recent investigations from the experimental perspective of searching for electron correlation effects in geometrically frustrated systems. And so what I'm going to tell you, I guess, is a relatively simple story from experimental perspective, which we think is also a pretty neat story. And essentially, we find a system, a platform, where we can find evidence for both geometric frustrated destructive interference induced flat band and also electron-electron correlations. And the combination of the two is what gives rise to non-Fermi liquid behavior and transport. So that's what we're going towards. So if we can begin by thinking about this question, how do we get to that regime where electron correlations is strong? We all know that we need U to be large and T to be small. And looking around for the systems that have been explored in our community, one way of going about doing that is to search in a regime where U is large, and as we know in the cuprates, which is a doping insulator. And also want to just also pinpoint that for multi-orbital systems such as the iron-based superconductors, where we have also studied, one can find the different types of correlation effect that depends on the orbital degree of freedom. So this is a purely a multi-D system, and here I guess I just advertised that we have studied the system to see that within the 3 T2G orbitals, you can realize in a regime where a particular orbital, in this case, DXY orbital, its effective mass can increase dramatically as you tune some sort of a non-thermal tuning knob. In this case, it's a substitution between tellurium and selenium, and you can see that the bandwidth or the mass enhancement grows strongly for XY, where other orbitals remain relatively the same. So we have also shown recently that as you go towards this limit, eventually you can actually enter this so-called orbital selective mod phase, where the XY orbital becomes completely localized. Right. So these are all manifestations of a large U regime. And another way to go about finding a large U over T is of course by reducing T. And these are the successful ways that have been demonstrated in our field. And one is, of course, the Moray physics, where you can fold dark bands and to give you mini flat bands with quenched kinetic energy. And also equally successful, if I may say, in the geometrically frustrated lattices. Here is shown for the Kagome lattice. One can achieve the same thing by utilizing this quantum interference effect to localize the electron wave function to give you quenched kinetic energy flat bands. So the advantage of going about in this route is that by this construction, both give rise to topological flat bands. And so the question then arises,